So somebody's taken a sample of a compound and they come back with these results. They tell you the percentage of fluorine, sodium, and silicon by mass in the compound. And now what you need to do is figure out the chemical formula of this compound based on the experimental results. That's what empirical formula means, from experimental results. Now you're not told how big the sample is. So in these problems, your choice of sample size is very important. And we've done some problems in which it seemed easier to choose a mole of sample. Well, you only choose a mole of sample when you have the chemical formula. We don't have the chemical formula here. And we're told the mass percents. So sample size for mass percent, to me, an easier one would be 100 grams of sample. Because if you have 100 grams of sample, how much fluorine do you have? Well, you have 60.6 grams. Now, even though we chose mass as our sample size, you have to get all of this into moles, because that's how a chemical formula is written. It's all about the moles. So let's convert fluorine to moles using the atomic weight of fluorine, using the molar mass. Let's keep going. Do the same thing for sodium. And do the same thing for silicon. Again, using the molar mass of silicon from the periodic table. Now, let's look what we have so far. What do these numbers mean? Well, it means, assuming 100 grams of sample, we have this many moles of each of them. But how do we use this to get the empirical formula? Let's step away from this for just a moment. Here's a sample that contains only oxygen and hydrogen. And after the analysis is done, these are the moles of each. And somebody else comes in with another sample, same compound. Then you run another sample, same compound, just 3 different sample sizes. Now, regardless of the sample size, if they're all coming from the same compound, there has to be one chemical formula. Now look at the relative number of moles of hydrogen to oxygen. What's the chemical formula for this? Well, if you compare the hydrogen to oxygen, you see that in each case, there's twice as much hydrogen as there is oxygen. Twice as much hydrogen as oxygen, H2O. That's the chemical formula. So it's not the absolute moles that are important, it's the relative moles that are important. Regardless of the sample size, for water, you expect there to be 2 moles of hydrogen for every mole of oxygen. And in this case, oxygen was our comparison. So that's what we need to do. We need to pick one of these for our comparison. These mole values need to be relative moles. Now, which one of these 3 do you want to pick? Well, you always pick the smaller one. That way, all your mole ratios are guaranteed to be at least 1. So let's compare fluorine to silicon. And when you do the math, the ratio of the moles of fluorine to silicon is a little over 6. And we'll do the same thing. compare sodium to silicon. And that ratio is a little over 2. Now let's look at those ratios. What are those numbers close to? The 6.01 looks pretty darn close to 6, and the 2.02 looks pretty darn close to 2. Now there are times where you have to really watch your rounding. In this case, these are so close to whole numbers, we'll just take those as our ratios. See, you've got experimental results here. There's bound to be a little bit of experimental error in here just due to measurements. So for our formula, we have 6 moles of fluorine for every 1 mole of silicon, 2 moles of sodium for every 1 mole of silicon. So F6Na2Si. For me, I don't really care what order you put them in, because you're not told anything else about the compound. It really is an ionic compound and is normally written Na2SiF6. It's called sodium fluorosilicate. Sometimes it's called sodium silica fluoride. But you don't know anything about that information, so this is sufficient. Now, when is close not close enough, and when are you not allowed to round those to the nearest whole number? When do you have to do further manipulations? Well, not in this problem, but the next problem I take a look at that.